So,
Sadece belgeleri.
Bir şey çıkmaya çalışıyorlar. Okay.
Liste vardır.
Hani Karaçay'ın İngilizcesi var ya. Yok.
thank you very much for being very patient, and I appreciate your standing and interest. We are pretty much done with the physics of our electron guns and the rest of the dynamics, and now we are fighting with the real world problems. Okay, let me show you. I have discussed this geometry in a bit in a very brief manner. Let me point out to you some aspects. This part here is cathode, which is actually the emitter. This part is the focusing cathode, and this part is the anode. Physics only deals with this thing so far, the physics we have discussed, by the way. Yes, but the rest of the things are equally important. Number one, you should have insulation between anode and cathode. The insulation, by insulation means that you have to operate it at 30 keVs or 50 keVs, maybe 200, 200, 100, 200, 300 even. So that insulation comes from materials. That material usually is ceramic in our case. Why ceramic? Because it is insulator, of course, but also is vacuum compatible. We are not free to use any material that can be insulator. Vacuum compatibility is perhaps the most important prime parameter or criteria when it comes to the selection of materials. It should not be degassing. It should not have pores. It should not be polluted. Otherwise, this guy is not going to work. Then you have micro welding here. You should provide your heater with low resistance path in order to have uniform heating of this gun. Unless you have unless you have a uniform heating, the distribution, the Maxwell's distribution is going to be disturbed, and your model will not follow, or the gun will not follow the model that you have assumed while designing this guy. Again, the feed-throughs are here. The feed-throughs are meant for providing the electrical signal to this part of the gun. So vacuum feed-throughs are also sealed to ceramics usually. And then you have mechanical, these flanges, which are CF flanges for ultimate vacuum sealing. And the whole assembly, of course, operates in vacuum. By vacuum, someone was asking this morning, we try to evacuate this machine up to extreme ultra-high vacuum boundaries, 10 minus 9 millibars, put it in pascals. Sorry.
Are you doing insulator in cathode and
because you have to provide the potentials. And the potentials are not usual, like they are, in any case, if they are potentials, if you don't have insulation between, there are some of the same potentials. So, and if we, okay. So we also use CST for another solution, that is to check if the ceramics are holding the high voltages. This is another geometry of the same thing, but this is just an adaptation. We can discuss it later when we discuss the problems that we faced. This is a geometry. The gun is somewhere here. The rest is a support structure and the insulating structure and the provision of high voltages and low voltages. We used CST to check if this guy is going to withstand the high voltage levels for high duty cycles even. But this is for DC simulation. What we do is we apply 10% when 20% higher voltages than operation conditions, and we check the potential lines generated by the electrostatic solvers. Once the solver is done, we analyze that, okay, this is the domain which is facing air. From this part, this is facing the vacuum. It is inside vacuum. The most vulnerable part is this coir to ceramic brace joint. And if there is a concentration of electric field here, then there is a chance of breakdown. In fact, we faced this breakdown in one of our guns, and we had to redesign the whole thing. So the limitation also comes, but luckily we have this tool available to us to assist in designing the ceramics for our particular job. Okay, we are done with this part, and now let's talk about the modern dispenser cathodes. I call it modern dispenser cathodes because they are pretty much advanced as compared to the usual tungsten or thoriated tungsten based guns. Okay, this is basically the source of electrons, the source of the powerhouse of the gun, and it is the most delicate part. It has so many conditions to operate that sometimes we are near to cry. It means it's very, very, very delicate part. And I heard that you guys are doing some research on dispenser cathodes here. Surely we would like to have a visit on it and see how it's done here. So let me go through a bit of this theory. The thing is that we should have a source of electrons that should provide us with uninterrupted supply of electrons, and that supply should be reasonable. 3 to 4 amps I quoted in the development of para-auxiliary theory. This is commercially available thing for DC operation. For AC operation, they claim that they can go up to tens of amps per centimeter square. Tens of amps is good enough for applications like microwaves and other things, but still. And then you have to operate it, you have to heat it to get to the level where the enough electron population is with you, and that temperature is usually around 1000 degrees Celsius. So the point here, so here, this point is to be heated up to 1000 degrees Celsius, even 1200 degrees Celsius at some point. It's a huge temperature, huge temperature. Rest of the parts should be designed in such a way that they should not degas. They should be able to withstand these temperatures. And then there should be a cooling mechanism of the guns. That's why you have coolant going through your vacuum devices, especially if they are operated in high duty cycle or even if they are operated in DC modes. Temperature control is different. Why? It is also important because if the temperature is accumulated here, because this part is in vacuum, this whole domain is vacuum, this is in air. Let's talk about the temperatures variation here. If the temperature is accumulating here, the only way of transferring extra temperature is through radiations. Believe me, only 5 to 10 degrees of temperature variation is going to affect the output of the gun. And you have to operate the stability. Remember that we are discussing the stability is one of the criteria for the stable operation of the gun. So we have to keep these guys at steady temperature. It is, I don't know, autopilot or something, but you have to be very careful in designing, and then we have to be extra careful in assembling these things. And then you should have a coolant flowing through. And this particular gun had a jacket outside which was cooled by the water, but we had to do some experiments in order to reach a stable operating point. But now we realize that there must be complete thermal analysis of the gun. Then again, this temperature is not going to stay because the rest are cool surfaces, they are not heated. And when the temperature goes through these ceramics, they start degassing. Degassing means poisoning. Poisoning means death. Sensor cathodes are very good, but they are equally delicate. We have to have a monolayer of barium over tungsten in this particular design. Monolayer means single atom layer. And if oxygen comes from somewhere, if hydrogen comes from somewhere, water molecule, the worst thing, comes from somewhere, then this guy is going to stop its work. And you see and you can easily imagine the bank or the sources of such poisoning in this gun. So you have to be careful while manufacturing, you have to be careful while assembling, we have to be careful while conditioning. We slowly condition it, we slowly allow it to degas whatever it has. So if the ceramics are not controlled porosity-wise, if the metals are not very pure, forget about the functioning of your gun. You have invested maybe 3 months, 6 months designing, invested a lot of money, but in the end, if the choice of materials is not wise, I'm sorry, it's not going to work. Tungsten can emit high electrons, high rates of electrons, but that is at even higher temperatures. It's around 2000, 2200 Celsius, 2400 degrees Celsius. But that temperature range is even going to kill it more. But for low temperatures, that is, they're not too low, the 1000 degrees Celsius thing, even then, it is very, very hard to maintain the temperature stability and to remain this thing. To remain in this region, the ultra high vacuum region is literally a challenge. It's not impossible. We and many others do it, but of course, this is the condition that you can do, that should be met. I always talk to my group mates, and my group mates always talk to the rest of the world that let's be patient, let's be disciplined. But the clients are not always in this mode. But this is the condition that has to be met if you want to have a seriously working electron source. Charge density, that is that is to be obtained, usually it's tens of amps. In our particular case, we are able to have 2 to 2.5, maybe sometimes 3 amps per centimeter square, but it's square. I'm sorry, but it should be red square. It also has limited lifetime. Limited lifetime, this line should be clear, this sentence should be clear when we will discuss the working of dispenser cathodes, because the dispenser cathodes are a mix of things. It is just like mixing of materials in order to have higher densities of current at lower temperatures. We mix barium with tungsten to have higher densities at low temperatures. But barium is stored in a reservoir, and that has a limited supply. So of course, but as I mentioned this morning, this lifetime is not that short. The ones which we are using, the manufacturer claims it's around 10,000 working hours if wisely used. Wisely means all the conditions of operation are met. Electrons emitted have thermal velocities, and cathodes are vulnerable to poisoning. Thermal velocities, temperature stability. Temperature stability is utmost requirement. Believe me, it is not a job of a kid to do such things. And contaminations, if they are there, even if the cathode is working. Imagine your gun is working, everything is fine. Suddenly, some accident happens. Accident doesn't mean that you have to collapse everything. Some sort of packet of gas is suddenly released in the system. It will contaminate within a fraction of a second the cathode, and your gun will stop working. This has happened tens of times to us. When we had some accident, the vacuum got lost, means it exited extreme ultra high vacuum or ultra high vacuum range and went to high vacuum range, meaning thereby that if you have a vacuum operating at 10-8 millibars or 10-8 torrs, to let's say jumps to 10-6. Even if it's still a vacuum, it's a reasonably good vacuum for many applications, but it is the dead end for your gun. So the pressure at any cost must not exceed 10-6 millibars. This is the upper limit. That's why we incorporate in our control a very strict limit. We have limited to 5 10-7. Remember, it's a logarithmic scale.
-6 bars or millibars?
-6 millibars.
10 to -9 bars.
Yes.
-10. Yes, 9 to 10 millibars. Bars.
Let's go to a bit of theory of thermionic emission, but I guess it's straightforward. That we have metals which have valence band and a conduction band. If it's a vacuum here, then you can introduce some energy to the electrons so that they can escape the system and become part of the vacuum, and that energy comes from the temperature. The Richard-Dissman equation very well explains this thing. So you have to give the temperature to your system, and that temperature is going to energize the electrons. By the way, someone was asking me the temperatures. Temperature has a very different meaning to a physicist than it is to engineers. Any physicist can tell me what is temperature. I was almost got killed when I told that temperature is this thing. Temperature is the average kinetic energy of the system. Statistical thermodynamics. So the electron temperature is different. Electron temperature is very different. The plasma temperature is different even. So this temperature should not be confused with this 100C, 1000C, or whatever. But anyways, this is the average kinetic energy which is imparted in the system. Of course, in real world, we always have that Celsius, Fahrenheit, and Kelvin scales, and this is, of course, the practical thing. But here, one should be seeing that this is statistical equation. But in real world, we can translate it into in terms of a bit of rearrangement, and then we can see a linear plot, and we see, okay, we give our system a certain temperature in order to have a certain density in terms of the density of states. Those who are hardcore physicists, they say, okay, this is density of states, to be precise. For engineers, 1000 Celsius is okay. But how do we do it? Okay, let's go through this chart. I copied it from a book. Tungsten, 4.6. But for that, you need 35 at 400 Celsius. It's going to melt your system. It's going to melt your system. Many, if you're really after something. Barium is reasonably good. Osmium is also good. The ones which are highlighted in red are the ones which are widely used. So we can mix barium with tungsten to have a reasonably good dispenser cathode. How do you do it? Okay, this plot is needs some attention. Say, for example, you have your valence band, and if you apply potential, the work function on the surface is reduced. I would encourage you to go through this slide, because then you will, the applied potential is in red. You see the work function is reduced if you apply the incentive. It's just like if a baby is sitting in a cart and it's not able to jump over, so you extend your hands, so you just come. You extend your potentials. So the baby is coming from the cart to you. So these electrons can be perceived as babies, and this potential is your extended arm. Simple. Now, the construction of a dispenser cathode. Please, let's invest about 10 minutes on it, or maybe lesser. We have tungsten matrix. We have porous tungsten. The porosity is around 98%. In some literature, I've seen 85%, but it varies from manufacturer to manufacturer. And then we have a reservoir which is filled with barium, strontium carbonates. In fact, it's not the complete recipe. I will give you the reference of the book. You can go through the data. It's a standard thing. It's barium carbonate, calcium carbonate, aluminum oxide, mixed in certain ratios. These are mixed with certain ratios and put it in this reservoir. And then this maroon, we call it maroon or red part, this is the porous tungsten, and then this is slowly heated. When it is slowly heated, the barium oxide is converted in barium carbonate is converted into barium oxide on first step. And then this barium slowly seeps through this porous tungsten. Someone was asking me the other day, not here, what is the seepage rate? Let me recall. It's 1 angstrom per 3 minutes. In 3 minutes, the seepage rate is 1 angstrom. And imagine if this disk is around 3 millimeters thick. You can appreciate this is the outer boundary. can you distinct the disc is, can you see the disc is braced to the rest of the body? It's just like cap on a bottle. Can you see it in the photograph? Yes. Okay. So this is the porous tungsten. Under it, you have a reservoir which is holding your barium, and that barium is slowly heated, very, very, very slowly heated. The aim is to deposit a monolayer of barium over it. Unfortunately, free barium is reactive. That's why salt of barium is used. But for this, you have to do all the chemistry under vacuum. So all the chemistry under vacuum is basically done very slowly by very slowly heating this guy. You have a heater, and usually you have two. Okay, imagine that you have a heater like this. It's a spiral, but again, you have to counter. The heater should be wound and have an additional counter direction winding. Can anyone think why they have double the winding, and why the outer winding is counter the inner winding?
Inductance.
Yes, inductance method. Thank you very much. Why it is important? Oh, you have to have a heater anyways. Professor Yaqub was mentioning the magnetic field. Yes, the magnetic field. So imagine the delicacy of this this instrument. It is just like, it's just very thin, thick. Probably I can fit one in on my nail. Even then, the heater is wound, because you cannot even tolerate the fluctuation of magnetic field on the surface, because eventually the barium is deposited like carpet, and the carpet is only one atom thick. I don't know, we should be using the word thick on it, but it's the height or the thickness is just one atom. Monolayer, yes, monolayer of it. Vacuum is very important, and then we have to assemble it very carefully on the ceramic, and that ceramic is eventually fitted in the rest of the gun assembly. The whole thing, since it reaches to very high temperature, is confined in molybdenum cylinder, and the heater wires are going through this. They are isolated from this, from the outer world. They are just heating up, and this yellow portion is a potting, aluminum potting. Aluminum is a very ceramic potting. Alumina. Yes, thank you very much. Alumina is a very good conductor, but it's a very good insulator. So this is going to heat up. First, it's just like starting a diesel engine. The first few voltages will induce a cloud of everything comes out for a very fast. So this activation process, we call it activation, is basically converting, is the process where we convert the barium carbonate into free barium to be used here. I have written an equation here. This is pretty much the recipe, but the chemistry is and sub-zero level in chemistry, so please don't ask questions. Barium oxide, barium carbonate, just to have a higher uniform heating, this is mixed with calcium carbonate and aluminum oxide, alumina, and the powdered form is then heated, and when it's subjected to tungsten, it is forming monolayer of here. This is the cross section of the porous tungsten. You see the machining, it's already very rough. It's already very rough. It is our life. I mean, it's made of powder. It's made of powder, then it's sintered, then it's machined. But again, this is not the real world. Again, this is a cartoon of on our right hand side. These black parts are basically this barium carbonate. They are seeped when are heated. This slip through these openings, not openings, pores, and then they are deposited on this side. This is like buttering your bread.
This barium coating is replenished during the operation?
Yes, it is replenished during the operation, and that's where the life comes. The reservoir is constantly supplying, and the seepage rate is I just mentioned
An angstrom.
angstrom per 3 minutes. When they are manufactured, the manufacturer already impregnates the disc with this barium, and during the rest of the life, this reservoir is used. Okay.
इसके storing conditions क्या है?
The gentleman is asking the storage conditions. They are ideally stored under vacuum, and they are shipped under vacuum, but they are not that sensitive. They can be regenerated. Okay, this in fact is a very good comment. I almost forgot to mention. Thank you, sir. Usually, when people were working with cathodes, they used oxide-based cathodes. Once those cathodes are exposed to air, they are finished. They cannot be regenerated. The chemistry cannot be redone. This is not reversible process. But here, if some accident happens, unless you just burn the cathode right away or break it to a point where you cannot do something. But if the surface is contaminated, when I say contamination, means that the barium layer is polluted, or the surface of the cathode is polluted with some contamination, then you can go to the conditioning cycle again, and the thing is fresh. So remember the point where I mentioned that it should be cost effective, it should be replaceable. If something happens, you should be able to recover it. That's why those modern cathodes are coming with this feature. If something happens, if your system is down, you can recover it in more or less in 2 weeks. Yeah, 2 weeks should be enough time to recover it. You first have to go through the vacuuming, and then you go to the conditioning. Conditioning means the slowly heating of this device, and then it should work. When it is meant to be exposed to air or stored, what we do is we purge our system to nitrogen or any inert gas, because then the monolayer which is formed is not poisonous. Of course, we have to go through the activation cycle again, but that activation cycle is lesser extensive if the exposure has been to nitrogen. Okay, we have gone through this potential thing already, but let me show you this thing. The emission density varies with different types of cathodes. For example, if osmium, that you recall the table which I showed a few slides back, osmium, rubidium can be coated on this, so the efficiency is different, the temperature time is different. And if you operate your cathode at higher temperatures, no matter, it's very convincing that you get to very high amps per centimeter squared, but your life is compromised. The percentage of current is there, but the life goes away very quickly. So this graph is showing the vacuum conditions that are required. Excuse me. This is perhaps the first graph which I always refer to. I encourage of my younger colleagues and students to at least have a detailed look on this thing. Please invest a couple of minutes on it. Here we have pressures or vacuum.
Here we have the number density of nitrogen or ideal particle, sorry, not nitrogen, ideal particle, because it's again statistical thermodynamics that is built on some ideal hypothetical particles. And these are the mono time which would take for the formation of a monolayer of that particular ideal particle. So we operate between 10⁻⁶ to 10⁻⁹ torrs. And in that case, if something happens, the monolayer will take around 2 minutes or 1 minute to form. In case of accident, something comes through, the monolayer formation time is around two minutes. Okay. Even at that type of pressure, we have a very high density, 10 to around 13 particles per centimeter square, per centimeter cube. So the guns, you cannot have perfect vacuum. Huh? So we always prefer to work in this region. This is the deadline, meaning that if the particle density crosses 10 to 13 per centimeter cube, forget about the working. You have to go again. So vacuum technology is a whole lot of subject. I would encourage you to go through this. How do you manage it? But it's not the very subject of my talk. Perhaps someone can discuss it, because it's a vacuum electron devices school. So vacuum comes first. So this is the temperature. This is the higher end of our operating conditions, and even then you have a molecular density very high. Mean free path is okay, good, and around tens of seconds it takes to make a monolayer. You can find this in the reference called Vacuum Technology by Roth. It is the first text that I read in my university, but it's a very good book. Okay, fabrication and integration of the electron guns is important. Once the things are back from the workshop, we go to the assembly of the gun as per the actual drawings which we conceived. The guy who was asking questions, he is a brilliant colleague of mine. He was my student and now is pursuing his PhD in Italy. He is an artist, and he actually assembles this, usually assembles these cathodes in this gun. We together work, but some hands are perhaps naturally gifted. So the alignment is done, the things are done, and we have this assembly here. But be careful. Electrodes have to be very precisely manufactured. The alumina, the quality. I'm emphasizing on alumina again and again because it has pores. Whenever there are pores, they're not sintered, there is a chance that it will degas. Degas means poison. Poison is not allowed.
It's glazed or not?
It's not glazed.
Not the.
It's not glazed.
Is there an effect positive or negative for glazing?
Sorry?
Is there a positive or negative effect of glazing? Maybe.
Yes, glazing I would prefer for non-glazed, because glazing can have sputtering effect at some point, and then the sputtering thing can actually pollute the environment. Glazing is very good if the outer ceramic is glazed. For example, ceramic housing can be glazed. It will protect it from dust and many things. Yes, and then the insulation is improved. But inside the vacuum, I will not go for that.
Kashif, for certain application, we make very high density aluminum ceramic, 98+%.
Okay.
Theoretical density.
Yes.
So, did you try that?
We approached to the guys who do it in Pakistan, you know already. So they say that okay, if you go to higher percentages, then the post processing is perhaps difficult, but that makes life difficult for us. So maybe you can add some.
I can talk to.
Yes, thank you. That will be a great help. Thank you. So your gun is done, your physics is okay. Let's go to the evaluation, how it's performing.
Before we skip, to the other subject, why don't we use cold cathodes, like field emission, cesium is typically used.
Yes.
I mean, you wouldn't have all these temperature-related problems in your case. High temperature.
Yes.
And also the
I'm not
emissions
really
maybe
a user. At a point we tried to use field emission. For example, in magnetrons, they prefer to use it. And yeah, but there you have plume of particles going everywhere. Particles means electrons going everywhere.
But you can.
Yes, collimator.
Dynamics.
Yes, but personally speaking, we did invest about 3-4 months on this subject, but perhaps we are. I'm not really a user. My comments should not be taken that seriously, but my knowledge is limited in this case. But the thing is that the vacuum is disturbed a lot in that case. Perhaps we were not very practicing nice thing. We were using carbon nanotubes with a certain chirality for field emission. And that field emission is efficient in terms of current that is produced. Of course, you're absolutely right. But with the period of time, the erosion of the cathode was very, very fast, rapid. And secondly, the eroded particles were everywhere in the system. Our particular job was to have a system coupled with the LINAC so that the debris goes down the LINAC and pollutes the cavities. So
contamination is the
contamination was basically, yes.
I recently read a few articles about coating the ceramic with titanium nitride.
Secondary electron emission. Yes, nitrides are poisons. Nitrides are poisons.
Ceramic windows are also.
Yes, ceramic windows are also coated, but there you don't have beam. It's there is no beam inside.
But there is no direct beam touching to or hitting at it.
But there's a probability of touching something, and if some arc happens here, sorry. If some arc happens here and you have nitrides here, the nitrides can easily flow. You have vacuum. So nitrides are one of the poisons.
These classic cathodes you manufacture yourself or you?
No, we get it from the market, international markets. We are looking forward to have some. If I have time, I can perhaps invest some time. In fact, I tried to pursue a couple of students, but they were not interested. We are limited with time. We are limited with manpower, so it's one of the things. Maybe that's why I was asking Professor to perhaps visit the laboratory where you guys are doing it. It will be nice.
We are arranging.
Yes,
We are arranging for tomorrow.
thank you very much. But it will be very nice. Maybe we can learn something. Maybe we can contribute to that part. That will be a great help because the provision of this dispenser cathode itself is a big problem. Testing and commissioning. Your gun is ready. Okay, now you have to have vacuum system. You have to couple it with it and try to have something which will be doing the evaluation of the state vector. We come again to physics. Because the character, the quality of the manufactured thing is parameterized by the state vector. I think we are almost close to the lunchtime.
I will just describe this setup of our laboratory, and the results can be discussed in my last session. Is that okay? Do we have time until lunch?
Yes, we can continue.
10 minutes more. So let's invest some time in lab. Okay, this is our lab, and many students and many junior colleagues have contributed in this thing. For example, Schwab, who was talking to us this morning, maybe he's listening today now as well. His part was the contribution on the development of cerium yak screen. When he was an MS student, he developed this screen. One of his colleagues worked on the development of high power Faraday cages, Faraday cups. Now my students are working, this is an old picture, three months back picture. They're working on the development of beam position monitors. So we have extended this, and beam position monitors are installed downstream. We have magnets. We have a very strong manpower who is working on the development of electromagnets, the focusing and steering, and then this part is BCT. The only perhaps imported part is BCT, and the rest, of course, is purchased. And this inverted magnetron gauge, the diagnostics basically is homemade, as is the electron gun. So the electron gun is first evacuated from atmospheric pressure down to 10 minus 7 millibars, sometimes 10 minus 6 millibars, and then we have to bake it. Bake the system is the recipe. Bake it to 400 Celsius ideally, but we are limited due to many constraints, because you cannot bake everything at a uniform temperature. You have to be careful, otherwise some brace joints will just fail. Or if you have white on rings in the system, this will also be a collapse. So you have to bake it gently. We usually go up to 200 Celsius. 120 is the average range where we operate. So many cycles, perhaps 3-4 cycles, will give you to the point where you can switch on the ion pumps. Ion pumps can be switched to 10 minus 4 millibars, but they will not be as efficient as they should be. So because ion pumps are the banks, they will not spit out, gather and spit out. They will gather everything. So they age very soon if they are operated at higher pressures. So ion pumps are switched to the system, switched on when this line is reasonably at a good vacuum. We have a whole setup of pulsed power supplies. Unfortunately, I've not shown it here, but imagine that you have an insulator system, you have DC power supplies, you have controls. All this is remotely handled. Maybe it's a DC or a pulsed operation, and even the low voltage operation. I will stop here. Maybe, okay, just the last slide before lunch. This is the connection. We have to supply our heater with the low voltages. Our power supply is isolated and shut down, and that power supply is basically heating up this cathode to a temperature where the chemistry can happen. My colleagues, especially my bosses, ask, don't tell my bosses, they ask, how long will it take you to get your gun activated? I don't have any answer to it. No one has any answer to it. There is no perfect recipe. I'm stealing this phrase from the manufacturers. The bosses are bosses, you know. So there's no, it depends on the cleaning, the degree of cleanliness you have, the operating conditions you have, and every gun is unique. Every system is unique. Every operating condition is unique. Because you're not dealing with the monolayers. It's not the bulk It's the monolayer. It's the nature has given you the opportunity to play at the atomic level. In atomic level, the whole physics is different. That's why perhaps they invented the nanotechnology or something. So, and you also apply your pulsed or DC on this thing. Is this a mistake that I'm applying DC HV on filament? No, it's not.
Yes.
Yeah. It's not a mistake. This diagram is perfect.
Maybe anode.
The anode is grounded, but I'm also supplying HV. In fact, shortening the HV to LV. Cool. This is a very subtle concept. We will discuss it after lunch. So for now, imagine this is the electrical setup that we require, or the circuit diagram that is required for a successful operation of the electron gun. Thank you very much for your patience, sir.
Negative voltage cathode before after cathode is one accelerating voltage, but back side to hold electrons inside the behind of the cathode. So make a pulse with control cathode voltage.
Yes,
Accelerating.
yes.
voltage.
This is of course it's a right concept that the reason to this is a bit different. We have to. You have
They accelerate.
yes, yes.
The grid is afterwards, after the anode. So you apply that pulse.
Yes,
to the
yes,
grid.
yes.
This is, but imagine I give you a clue. Imagine this wire is not connected with the LP.
Yeah, yes.
This is at, let's say, a few volts, 6, 7 volts, and the body is at 30 kV. It's going to short. Oh, sorry. It will be an explosion. You have to connect it with the LV power supply to HV. How it's going to work? Electrical engineers. Let me add one. You should be able to answer. The isolation transformer. The isolation transformers are the essential components of the operation. So let's have lunch. Bon appetit. After some.
Yes.
Thank you.
The light is continued until 2 p.m. and we will continue to another lesson with Ahmet Ercan. See you.